torque about a point. Okay, torque produced by a force about a point is calculated or is expressed as tau is equal to R cross F. Okay, and torque about an axis, okay, is calculated as component of torque. Okay, is equal to R cross F along that axis. Let's apply both of them and calculate torque. Okay. Consider a situation like this. Let's visualize X, Y, and Z axis. Suppose there's a force acting, okay, at this point. What are the coordinates of that point? It's on the x-axis clearly. So let's take the point as 10, 0, 0. And how is the force acting? Let's say the force is acting at that point parallel to the z-axis. How much force shall we take? Say 20 newtons. And if this is the positive x direction and this is positive y, then this out of your screen will be positive z. Into your screen will be negative z. So the force 20 Newton is acting into your screen. Fine. Now, let's say there is an object, you can imagine a cylinder to be present here. And let's say the cylinder is free to rotate about the y-axis. Imagine a cylinder like this. Okay. Now you are applying a force along the surface of the cylinder tangentially. Then what will happen? You know that the cylinder is going to spin like this. So there will be a torque produced this way. Okay. So this cylinder can rotate about the y-axis. That means this force can produce torque about the y-axis. Okay. Now our aim is to find out how much torque it produces about the y-axis, and we'll express that as a vector. So what I'm asking you to calculate is torque produced by this force about y-axis. Okay, not a single point, but an axis. Fine. Let's try different approaches. First thing, I just told you that if you want torque about an axis, okay, you can take any one point on that axis. Okay, let's call this point as P. You can take any one point on the axis as the reference. With respect to that point, you write position vector of the point of application of the force. So we'll call this as R vector. Okay, and you have the F vector already. Then what you do is calculate tau is equal to R cross F. Okay, and then take its component along y-axis. Because you want torque about the y-axis, no? So you have to take its component along the y-axis. Let us do this. Okay. Aishwarya, tell me what coordinates you wish to take for this point P. It's on the positive y-axis. Keep that point in mind and assign some coordinates to it.
0, 8, 0.
0, 8, 0 you want to take. Okay. So basically we are taking a random point on the axis about which we want the torque. Okay, that point is 0, 8, 0. Fine. And the point where the force is being applied, let's call it as point A. That point is 10, 0, 0. Okay. Rishi, tell me this. Tell me how to express this position vector R of A with respect to P. That R bar vector is there, no? How to express that?
The 10 I cap plus 8 J cap.
Why will it be 10 I cap plus 8 J cap? 10 I cap plus 8 j cap, I'll help you visualize. 10 I cap is this way, plus 8 j cap is this way. So 10 I cap plus 8 j cap will be like this. That is not our vector. You need to express position of A with respect to P. Okay, basically relative position. And position of A with respect to P is the actual position of A minus the actual position of P. Simple. Okay. What is the actual position of A? 10 I cap. What is the actual position of P? P is on the positive y-axis. J cap. 8 j cap. That's all. This is the relative position vector that we have to use now to find out torque about that point P. Not directly about the axis, but about point P. This vector has to be used. Okay. So 10 I cap minus 8 j cap is the position vector of the point of application of the force with respect to the point P about which you are finding out torque first. Okay. Now, can one of you tell me how to express this force in terms of I cap, J cap, K cap? As I said, it's acting into your screen. Okay. In the diagram, it looks like that. I mean, just to show you that it's parallel to Z axis, I have drawn it like that. It's acting into your screen. How do you express that as a vector?
So minus 20 kg.
That's all. Negative Z direction, 20 units. So the vector is minus 20 K cap. The force vector is minus 20 K cap. Okay. You have the position vector 10 I cap minus 8 J cap. And you have the force vector minus 20 K cap. Take their cross product now. Torque about the point P is what we are calculating. So you will need position of A with respect to P cross the force whose torque you are calculating. Position is 10 I cap minus 8 J cap. Cross the force whose torque you are calculating is minus 20 K cap. Okay. Calculate this cross product quickly. I got two answers as 160 I cap plus 200 J cap. Let's see. First is 10 I cap cross minus 20 K cap. 10, 20 is 200. Now K cross I is J. I cross K is minus J. And there's another minus sign here. Okay. You are doing I cross minus K. Okay. So minus of minus J becomes J cap. Fine. Next. Minus 8 J cap cross minus 20 K cap. Minus minus get cancelled. 820 is 160 and J cross K is I. Okay, fine. So the torque produced by this force about the point P is 160 I cap plus 200 J cap. Visualize this. Okay, it will be in Newton meters. 160 I cap plus 200 J cap. It's in the XY plane. Okay, so X component 160, Y component 200. X component 160. Y component 200. Okay. 160, 200, maybe like this. So this is the direction in which the torque is produced. Now, what does this mean? What does it mean by producing torque in that direction? It means this force about this point rotates or produces a rotational effect about this axis. Okay, the force tends to rotate the object like this. Okay, had it been a free object, it would have rotated about like this actually. That is what it means. Okay, but this cylinder is not a free object. Fine. Or whether it's a free object or not doesn't matter. We want torque about the y-axis. How much rotational effect it has about this axis is what we want to find out. So imagine the cylinder is restricted to rotate around this axis, the y-axis. So this tilted motion will not be allowed. it can only, if the cylinder has to rotate about the y-axis, it can only rotate in the xz plane. Okay, it can only rotate like this if it wants to go around the y-axis. Fine. So that torque is what we want to find out, and this force can make that also happen. Okay, so how much effect does it have in making it rotate that way? Let's find out. Okay, now we got the total torque about the point P. I told you, if you want torque about an axis, find out torque about some point on that axis. That part we have done. Then take its component along the axis. Now what axis are we talking about? Y-axis. This is the total torque about the point P. Now tell me, Rishi, you tell me, how much is the y component of this torque? 160 I cap plus 200 J cap. What is the y component in it?
200 J cap, sir.
200 J cap. So 200 Newton meter is the torque produced by this force about the y-axis. So this force produces that much rotational effect about this axis. That is what it means. Okay, so what we did here is we took a random point on the axis, found out torque about that point, and then took torque's component along the axis. Now, last class I told you another way also. If you can visualize the perpendicular vector drawn from the axis to the point of application of the force. Okay, if you can visualize this vector, let's call this as r perpendicular bar. Then directly that vector cross the force will give you torque about that axis. Okay, let's see if that also happens or not. Can one of you tell me, okay, how to express this r perpendicular vector? You can see I am drawing it from the origin to the point A, where the force is being applied. How to express r perpendicular in terms of I cap, J cap, K cap?
10 I cap, sir.
Simple 10 I cap, correct. Okay, and the force is minus 20 K cap. So if you do r perpendicular cross F, 10 I cap cross minus 20 K cap, you directly get 200 J cap. That is the torque about the y-axis. Simple. Okay, so that
Sir,
is
I
what
have a small confusion.
tell me.
When they don't give us like R component parallel or R component perpendicular, how do we exactly determine it? Like,
How exactly you can find out? See, they have to give you something about where the force is being applied. If you know where the force is being applied, then a little bit of geometry will help you write that r vector. Without telling you where force is applied, they cannot ask you to calculate torque.
oh, okay, sir. Understood.
They should tell
Yeah.
where the force is being applied. Yeah. Fine. Now see, this force was in the z direction. Okay, and the perpendicular vector was from origin. It was along the x-axis. So one, like r vector is along x-axis, force is in the z direction. If you take their cross product, you will get cross product in the y direction only automatically. Suppose the force was not in the z direction. Let's say it was like this. Then what to do? Okay, then again you take the cross product and take its component along the y-axis. Okay, so if you are given the force as a vector and if you know the point of application of the force coordinates, this is how you calculate torque about an axis. Okay, but mostly you will not be required to calculate like this. Okay, in a particular situation, you will be shown how the force is acting. Based on that, you will have to calculate torque. For example, this situation that you see on your screen. There's a rod. You know the axis is passing through one end of the rod and it is perpendicular to your screen. Okay, perpendicular to your screen means it's like the z-axis. The rod is in the x direction. Okay, rod is placed along x-axis. Force is being applied along y-axis. So r vector is in the x direction. Force is in the y direction. You take the cross product, you will automatically get it in the z direction. Okay, so that way you will be able to find out torque in most situations based on how the force is acting. Let's discuss some more cases. Consider this now. Okay, let's use this coordinate system itself. Okay, in fact, let's visualize a cylinder again. The cylinder is restricted to rotate around the y-axis. Okay, so let's say they have made an axle such that the cylinder can only rotate around that. Now, if you apply a force along the x-axis, okay, so let's say you attach something to the cylinder here and apply a force like this. Tell me, will that force which is acting along the x-axis make the cylinder rotate around the y-axis? Force is exactly acting on the x-axis. I'm not saying it is parallel to x-axis. It's exactly along x-axis. Can it make the cylinder rotate around the y-axis?
No, sir.
Okay. Aishwarya, what is your answer?
Sir, no.
It cannot. Okay, that is correct. How are you able to say that? Vanilla, you tell me, how are you able to say that it will not rotate the cylinder about y-axis?
Sir, because if you calculate torque, it is not in the direction of y.
Okay, if you take a position vector and calculate torque, you won't get a y component. Makes sense. Yeah, you take a random point somewhere here. This becomes the position vector of the point of application of the force. That position vector is drawn from y-axis onto x-axis. So it's in the xy plane. Force is in the x direction. So position vector in the xy plane, force in the x direction. If you take their cross product, no, you'll get in the z direction. Okay, r cross f will be in the z direction, which won't have a y component at all. A vector completely in the z direction won't have a y component. Okay, technically, yes, that way you can answer. But a simple way in which you can answer is, if the force is applied this way, the line of action of the force cuts the axis about which you are trying to find out the torque. Okay. In the last class also, when we first discussed about torque, we had come across a situation like this. Yeah. So I asked you to imagine this as a door being viewed from above. And I asked you if this force can rotate the door. It cannot. Okay. Why? Because if you extend its line of action backward, it cuts the axis. Okay. Or it intersects the axis. So remember this point. If the line of action of a force intersects an axis, it can never produce torque about that axis. Impossible. Okay, because if the line of action of force cuts the axis, it means the axis and the line of action of the force are in the same plane. It means the axis and the point of application of force are in the same plane. Okay, point and line also. Right? Then if you take r cross f, it will never have a component along that axis. So if the line of action of a force intersects an axis, it cannot produce torque about that axis. You can visualize it like this also. Fine. Yeah. Consider this textbook, all of you. And okay, I'll have to show you an axis. Now, this edge of the textbook, I'll take as the axis of rotation. So I'm placing a blue pen here. This blue pen is the axis of rotation for us. Okay. So this book is free to rotate about this axis. Let's assume like that. Okay. And this black pen will show us the way we are applying the force. Now, if you apply a force this way in the same plane as the textbook, so it's like if I pull it this way, fine, to my left, the book will have a tendency to move in this direction but it will never have a tendency to rotate this way if I pull it like this. Okay, why? Because this force, its line of action intersects the axis, so it cannot make the book rotate around this axis. It cannot produce a torque about this axis. Okay, so if the line of action of force passes through the axis, it cannot. Let's assume it is like this. Let's say the force is applied this way at an angle, still in the plane of the book itself. If I apply force like this, if I pull the book at an angle like this, what will happen? It will have a tendency to rotate like this. Fine. Rotating like this means what? It's rotating about the z-axis. Okay, but it's not rotating around the y-axis. So if the force is applied this way also, its line of action still intersects the axis, as you can see. Okay, and therefore it cannot make it rotate around this axis. It can make it rotate around some other axis, but not this one. Okay, so if line of action of a force ever cuts through an axis, that force cannot produce a torque about that axis. That is not possible. Okay, next let us consider this situation. Okay, you tell me this, all of you, or okay, I'll show you the diagram. Let's say this is the textbook and this is the axis. If we apply a force along this edge of the textbook, okay, now this force's line of action is parallel to the axis, so there's no way it will intersect. Okay, the line of action of force will not intersect the axis. Can this force produce a torque about this axis? Can this force make the book rotate around the y-axis? You all can try if you want. You hold one edge of a book and try applying a force parallel to the other edge of the book. See if the book rotates about the edge that you are holding. Think carefully or try and tell. What do you say? Vanilla, can that force make the object rotate around the axis that is shown?
No, sir.
No. Okay. Aishwarya, what is your answer?
Sir, no, sir.
Okay. Rishi, what do you say?
No, sir, it's not able to like.
It will not. About that axis, it cannot. It can rotate the object like this if you want. But this becomes rotation about the z-axis, not about the y-axis. Okay. Fine. So what do we understand from this? If the line of action of a force is parallel to a given axis also, it cannot produce a torque. Okay. So in this case also, torque produced by the force F is 0 about the given axis, which is y-axis in this case. Okay. Now, previous example, we saw that if line of action of force intersects with the axis, it cannot produce torque. Now we are seeing that if line of action is parallel to axis also, it cannot produce torque. Now it should not be parallel, it should not intersect. Then how else should it be? Okay. Neither parallel nor intersecting. Okay. You have to think in 3 dimensions. They are called skew lines. Lines which are neither parallel to each other nor intersecting each other. For example, you take these 2 pens. Okay. If I place them like this, they are parallel. If they are touching each other, they are intersecting. Like this, they are not parallel, but they are intersecting. Now you create some gap between them. Okay. So these are called skew lines. Fine. In such cases, the force can produce torque about the axis. It should not be parallel to the axis. It should not be intersecting the axis. Its line of action should be away from the axis. In that case, the force can produce a torque about that axis. And how you calculate the torque, we already saw. You take any one point on the axis, do R cross F, and then take its component along that axis. Okay. So why I'm explaining all this is because in many situations, you will first have to decide if a particular force produces a torque or not about a given axis. How to decide that? You imagine the line of action of the force. If it passes through the axis, no torque. If it is parallel to the axis, no torque. Neither parallel nor passing, only then torque will be produced. Okay. For example, in this case, okay, in this cylinder case, this 20 Newton force was acting in the z direction. Z axis is not parallel to y axis. And it's not acting through the origin, it's acting at some other point. So that line of action of 20 Newton doesn't even cut the y axis anywhere. Okay, so it's like the y axis and the line of action of this 20 Newton force are skew lines, neither parallel nor intersecting. Okay. Only in that case, torque can be produced. Fine, let's solve some more problems based on torque. Let's say there is a square plate. Assume its side is A. Let's say the square is restricted to rotate about this axis. The axis is the z axis. Fine. It's passing through the center of the square and perpendicular to the plane of the square. Fine. So I'll mention a few forces. You'll have to find out torque produced by each force about the z axis and then sum all of them to tell the net torque acting on the square plate. So its side is A. Just a moment. Imagine one force acting like this. You are given the point where the force is acting. You can even see the line along which the force is acting. Let's say this is 10 Newton. Okay, let's quantify all this, or let's call it F. Next, another force acting this way. The magnitude of the force is 2F. It's acting at an angle 45 degrees with one edge of the square. At one corner, it's acting at one corner. Okay. Then a third force acting this way. Let it be 5F. Fine. Calculate the torque produced by each of these forces about the z-axis and then calculate net torque. How do you calculate net torque? Once you know individual torques, if they are in the same sense, add them. If any of them is in the opposite sense, subtract. Okay. Try this, all of you. I'll give you 3 minutes. I got one answer as 3FA. Okay, let's see. Vanilla, can you tell me how much torque the force F produces and how you calculated that?
FA by 2.
Fi by 2, correct. How do you calculate that?
So the perpendicular distance between the axis and the force is half of this.
Okay, okay. See, in this problem, the square plate is in the plane of your screen and the forces are also in the plane of your screen. So you can assume that as the xy plane, all the forces are in the xy plane and you are asked to find out torque about the z axis. So the line of action of force is already perpendicular to the axis. Fine. Now, as I said, you can take r cross f or you can do r perpendicular multiplied with f. Okay, just get the magnitude. If you imagine the line of action of the force F, it is like this. And the perpendicular distance between the axis and that line is this. And that is A by 2. Therefore, the torque produced by the force F, let's call it as tau 1. It is F multiplied with A by 2. Okay. And Vanilla, what is the sense of this torque? Clockwise, anti-clockwise?
Clockwise, sir.
Clockwise. Okay, this force tends to rotate the square plate this way. Okay, just by visualizing we can tell. Otherwise, if you take proper R cross F also, you will see your right hand fingers curling clockwise. Okay, clockwise means the thumb will point into your screen. So minus K cap. Let's write it like that. That's the torque produced by the force F. Okay. Rishi, can you tell how to get the torque produced by 2F?
Sir, I'm not sure.
Okay, what all do you need to know to calculate torque produced by a force? The force is known anyway, 2F. What else do you need to know?
And the R vector, sir.
R perpendicular vector. Okay. R perpendicular is to be drawn from where to where?
Force applied to the point of reference.
See, you are talking about R vector as it is. Okay. Point with respect to which we want the torque to the point where the force is being applied. That is R vector. Fine, you can take that vector. It will be like this. But we are not looking for a vector now because we are not going to express the vector force in terms of I cap, j cap, the position in terms of I cap, j cap and solve. That will be a time taking process. What we'll do is we'll find out the magnitude first and then assign a direction to it. For magnitude of torque, you need to take force multiplied with perpendicular distance between the axis and the line of action of the force. Okay. Perpendicular distance between axis and the line of action of the force. First visualize the line of action of the force. This becomes the perpendicular distance. Can any of you tell me how much this distance will be in a square from center to one corner?
A by root.
A by root 2, correct. Then the torque produced by this force, the force is 2F and the perpendicular distance is A by root 2. And if you look at the way the force is acting, it tends to rotate this square plate in the anti-clockwise sense. Okay. If you take R cross F also, you'll see your right hand fingers curling anti-clockwise. R vector is from here to here, then turn in the direction of F. Okay, anti-clockwise. Anti-clockwise means out of your screen. So positive K cap. Next, torque produced by the third force. Aishwarya, can you tell me how much torque it produces? The force is 5F. What is the perpendicular distance and in which direction is the torque?
Sir, A by 2 into 5F.
Perpendicular distance is A by 2, correct. From the axis to the line of action of the force. So 5F into A by 2. What about the direction of torque?
Sir, anti-clockwise.
Anti-clockwise, correct. This force also about the given axis tends to rotate the square plate like this. Okay, anti-clockwise, so out of your screen. So K cap again. Right. So these are the torques produced by each of the forces. You add them vectorially, you will get the net torque. So the net torque will be the sum of these three. You can keep F aside. K cap also can be kept aside. In between, you will get first is A by 2, okay, minus A by 2. And then in second term, we have 2A by root 2, that is root 2A plus root 2A. And third term, we have 5A by 2. Okay, 5A by 2 minus A by 2 is 4A by 2, that is 2A. So the answer is 2 plus root 2 AF K cap. Vanilla, what mistake did you make?
Sir, I forgot to write root 2.
Okay, fine. Rishi, why were you not able to calculate torque?
Sir, I kind of got confused in the second one. The first one I was able to solve. The second one I
No, exactly what are you confused about is what I'm asking. The force is clear. The line of action of force is also visible to you. What were you not able to take?
got the distance from the center to the point of that wrong.
Okay. So geometric mistake. Fine. Aishwarya, why were you not able to answer? Where were you stuck?
Sir, I made calculation error in the final step.
Fine, fine. Yusuf, what was the issue? Why were you not able to answer? Okay, you find out and tell me where you are, where you are not clear. Now see, all these forces were in the XY plane. You are asked to find out torque about the Z axis. Okay, so it was easy to visualize the perpendicular distance and all. Suppose any of these forces were not in the XY plane. Let's say they had a Z component also. Okay, you imagine that 2F vector pointed slightly out of your screen. Okay, raised relative to your screen. Then also that 2F's Z component won't produce torque anyway. If any of these vectors had a Z component also, that component becomes parallel to the axis about which you are trying to find out the torque. Okay, that component won't produce a torque anyway. Okay, so if you want to calculate torque produced by a force about a given axis, visualize the component of force or the force itself in a plane perpendicular to the axis. Here, all the forces are in the plane perpendicular to the axis. Then it becomes easy to draw the line of action of the force, take perpendicular distance and calculate. Okay. Let's consider an equilateral triangle. Doesn't look like equilateral. Fine. Suppose the side of the triangle is A and it's pivoted at its centroid. Okay, so it's free to rotate around this axis which passes through its centroid. Can one of you tell me the definition of centroid? What does centroid of a triangle mean?
So it's like the center of mass only.
Ha, correct. Good that you thought in terms of physics. But in mathematics, what does a centroid mean?
It's like the x coordinates divided by 3 plus the y coordinates divided by 3.
Rishi, that's the formula. Okay, but there will be a meaning to it. No, what point is that? You are saying it is and you said it is intersection of
Medians.
Centroid is the point of intersection of medians of the triangle. Okay. What is orthocenter?
Intersection of altitude.
Point of intersection of altitudes of the triangle. Okay. Centroid, orthocenter. What other centers are there? Circumcenter will be there. Yeah, that's clear. Circumcenter is the center of the circle which consists or which passes through the 3 vertices of the triangle. What other centers are there?
Incenter.
Incenter. Incenter is the center of this circle, no? Which touches the 3 sides of the triangle inside. In circle and its center is in center. Okay. Okay, fine. Then there is something called X center also. You draw a circle like this, touching the three sides of the triangle outside the triangle, then it's X circle, X center. 3 X centers will be there for a triangle. Fine. Now in an equilateral triangle, centroid, orthocenter, circumcenter, incenter, they're all the same. Okay, for an equilateral triangle, they're all the same. Fine. Okay, let's say some forces are applied. One force acting along this side of the triangle, let's call it F. One force acting this way, call it, or let its magnitude be F by 2. And another force, a third one, let's say is acting like this, 2F. Calculate the net torque about the centroid. See, to calculate torque, you need distances. First of all, tell me, do any of you know how to find out this distance? The distance from a vertex to the centroid.
Sir, I'm not sure, I don't remember, but it should be like 2/3 or something of the height of the total height of the triangle.
2/3 of the median. Okay, correct. But how will you get the total length of the median? All the way from here to here, how much is it?
Root 3a by
Root 3a by 2. The side is a here. This angle becomes 30 degrees. And this is a right angle. You can use this right angle triangle to find out the height. Height of the equilateral triangle becomes a cos 30 degrees. That is a root 3 by 2. That is the height. And the distance from vertex to the centroid. Centroid divides the median in the ratio 2:1 from the vertex. Okay. So this distance that we are interested in is 2/3 of the height. Okay, fine. And here from centroid to the side of the triangle will be 1/3 of the height. Okay. Make use of these distances and find out the torque produced by each of these forces. Okay. Aishwarya, can you tell me how much torque this force F produces about the centroid and in which sense?
So root 3 AF by 6 K cap.
Root 3 by 6. Okay, fine. And K cap. So you are saying anti-clockwise. That makes sense. This force tends to rotate this triangle in the anti-clockwise sense. And how much torque it produces? The force's line of action is the base of the triangle. And distance from axis to the line of action is h by 3, 1/3 of the height. The height is a root 3 by 2. If you divide by 3, it becomes a root 3 by 6. So therefore, the torque produced by this force is F a root 3 by 6 anti-clockwise, so K cap. Correct. Rishi, can you tell how much torque the other force F by 2 produces? Second force.
So F a root 3 by 4.
How did you get F a root 3 by 4?
So I got the magnitude is F by 2,
The
and then
force is F by 2.
yeah, and then the length is a root 3 by 2.
Which length is a root 3 by 2? A root 3 by 2 is this complete length. Why are you bothered about this complete length?
Oh my God, my bad, sir.
You have to take the perpendicular distance from the axis to the line of action of the force. And in case of an equilateral triangle, this distance to any side will be the same. Okay, 1/3 of the height. Okay, 1/3 of height becomes a root 3 by 6. So the force is F by 2 and the distance is a root 3 by 6. So effectively the torque becomes F a root 3 by 12. And since if you see the force is acting this way, it tends to rotate the triangle clockwise. So minus K cap. Okay. Now the third one. Vanilla, you tell me torque produced by 2F.
FA by root 3, sir.
FA by root 3. Okay, fine. The force is 2F. And the distance to line of action, you can see it is again h by 3. Okay. That becomes a root 3 by 6. And since is this way, clockwise, so minus k cap. Okay, we got all three torques. You just treat them as vectors now and add. Let's make the, let's make the denominator common. So this 6, if you want to change it to 12, you add a 2, you multiply with a 2. This 6 also, if you want to change it to 12, you multiply with a 2 in the numerator. That's all. After that, it's just simplification. You will be able to do that. So understand how to calculate torque. You have to visualize the line of action of the force and the perpendicular distance between the axis and the line of action of the force. Okay.
There is the answer 3FA.
Wait. 2a root 3 minus a root 3. That becomes a root 3 plus 4. I'm getting 5f a root 3 by 12. Okay, wait. Minus. 2a root 3 minus a root 3 minus. So that becomes minus 3a root 3 by 12 k cap. 3, 4. I got minus a root 3 by 4 k cap. 2 minus 1 minus 4. 2 minus 1 minus 4 is minus 3. Minus 3 a root 3 by 12. I'm getting minus a root 3 by 4 k cap. Check if it is correct or not. Vanilla, where did you make the mistake, or did I make any mistake anywhere?
Sir, I did some calculations.
Okay, but this seems fine. No? 2a root 3 is here. There's a minus a root 3 here. 2 minus 1 is 1. And there's a minus 4a root 3 here. So 1 minus 4 is minus 3. Denominator is 12. So minus 3a root 3 by 12. Okay. Next, consider this situation. Suppose there's a rod. And you are given this as the axis. One end of the rod is, the rod is hinged at one end. Okay. And let's say there are multiple forces acting on it. I'm giving you all forces perpendicular to the rod itself. Let this be F. And where is it acting? At a distance, say L by 3. Yeah, 1/3 of the length. And there is an F acting here at midpoint of the rod. This is also perpendicular to the rod itself. And then there's another force acting here. Let its magnitude be 2F. You can see it's acting through or acting at one end of the rod, perpendicular to the rod. Okay, all three forces are perpendicular to the rod and you are given where they are acting. What I want you all to do is replace all these forces. Okay, there are three forces acting, no? Replace the forces with a single force, which gives the, or which produces the same effect as these three forces. Three forces combined. Now understand this point. Producing the same effect means the resultant of these three forces should be same as that new force with which you are trying to replace. So net force of these three should be equal to that new force. And the net torque produced by these three should be equal to the net torque produced by the new force. So first thing you have to do is, how much is the resultant force of these three vectors? Get that force first. Next, let's call this as FR, the resultant. Next thing you need to find out is how much is the net torque produced by all these forces. Whatever net torque these three forces are producing, the same amount of net torque that resultant force must produce. Okay. Now you know the resultant force from the first step. You know how much torque it should produce from the second step. If you know force and how much torque it should produce, you can find out where the force must be assumed to be acting. Distance you can find out. Okay. So the third thing is to find out the perpendicular distance where you will apply that force. Okay. Solve this carefully. There are two forces acting upward, one force acting downward. Find out the resultant of the forces first. After that, torque due to each force and add them as vectors, you will get the net torque. You know resultant force, resultant torque, get the perpendicular distance. Okay. I got one answer as net force. Fine, we'll see if it is correct or not. Rishi, you can see how the forces are acting. One force F upward, another force F downward, and another 2F upward. Can you tell me what is the resultant of these three forces? Or these three vectors? Aishwarya, how much is the resultant of these three vectors?
Sir, 2F upward.
2F upward, correct. It's like this force and this force cancel. And the only force which is not cancelled is 2F. And even if they don't cancel, you can write them as vectors and find out the resultant. Okay, this first force is like Fj cap. This is minus Fj cap. Minus Fj cap. And the third one is 2Fj cap. So you add all of them, you'll be left with 2Fj cap. So the resultant force is 2F in the upward direction or the y direction. Okay. Next, Aishwarya, did you calculate the net torque produced by these forces?
Sir, yes.
How much?
So 4FL by J.
We'll see. This force, the force F, which is acting close to the axis, it's acting along this line. The perpendicular distance is L by 3. So the first torque is FL by 3. Okay, let's use capital L itself. FL by 3. And the way it is acting, it produces anti-clockwise torque. Anti-clockwise is out of your screen. Out of your screen, you can represent it with K cap. Next, the force which is acting in the negative y direction, its line of action is at a distance of L by 2 from the axis. So it produces a torque of FL by 2. And the way it is going to rotate the rod is clockwise. Clockwise is into your screen, so minus K cap. Okay. And then the last force, its line of action is this way. Perpendicular distance is L. And the way it is going to rotate the rod is anti-clockwise, so K cap. 2FL, K cap. These are the three torques. Then the net torque will be 2 plus 1 by 3 minus 1 by 2. Okay. LCM is 6. 2 becomes 12. Plus 1 by 3 becomes 2 by 6. Minus 1 by 2 becomes minus 3 by 6. So 14 minus 3, 11. FL by 6. In the which direction? K cap direction, anti-clockwise. Is the net torque. Aishwarya, is this what you said?
Sir, no, sir.
Okay. Check your calculation one, but I think it should be this. Okay. 2 plus 12, 14 minus 3. Yeah. Vanilla, is this the torque that you got?
Yes, sir.
Okay, fine. So we know the net force is 2F. And we know net torque is 11FL by 6. We want that net force to produce this net torque. For that, where should that net force act is the question. So let's visualize what is happening here. The net force is in the upward direction, positive y direction. Where exactly to consider that is what we are trying to find out. Okay, let it act at some random distance x. The force is 2F. Let it act at a random distance x. Then the torque it produces is 2F into x. Because that x is already perpendicular to the line of action of the force, you don't have to take any components. And we want the torque to be 11FL by 6. That's all. F gets cancelled. You get x as 11L by 12. Okay. So 11 by 12 parts of the total length, or 11 by 12th of the total length. So it will be somewhere here. Like this. So a single force of 2F acting at this point in this direction or acting along this line produces the same effect as the combination of this, and this three forces. Okay. So this point that we found out, or this line that we found out, is the line of action of effective force. Fine. This way you can replace a set of forces acting on a system with a single force such that it produces the same effect. Now you may ask, sir, why take all that headache? If you want to apply any Newton's laws or anything to find out this, like, why should we even bother to find out this point? We know where individual forces were acting. We could calculate individual torques and use that in the answer, use that in the solution directly. Why replace them with a single force and again use it? Okay, you may ask that question. Actually, if you are given individual forces like this, you don't have to replace them with a single vector. Unless they specifically ask you to do that. You don't have to do that. But there are some forces which act at infinite points. Okay, and you need to know how to replace all of them with a single force. Otherwise, how will you keep calculating infinite different torques? Okay, what I'm talking about is the weight of a system. Okay. You consider this rod itself. Every particle of the rod has mass, and every particle that has mass experiences weight. Right? Now you all know from everyday experience that if a rod is placed horizontally like this and it is hinged at one end, okay, and you release it, you know it is going to start rotating. Okay, you release it from rest, it will start rotating. For example, like this pen itself, I'm holding it rigidly at one end now, so it's not rotating. But if I loosen my grip a little bit, it will rotate. Now from the horizontal position, if it has to start rotating, there should be some torque acting on it. Okay, torque is what changes the rotational state of a system, right? Now, can any of you tell me what makes the pen rotate this way? Which force makes the pen rotate after we leave it?
Gravity, sir.
Gravity. Because of gravity only it tends to fall down, but we are not allowing this end to move. So it has no other choice. It has to rotate like this. Okay, same thing happens with a simple pendulum also. Now, suppose you know the mass of this pen, then you know the weight of this pen mg. But when it is released from this position, that mg is producing a torque and disturbing its state of motion. If you want to find out how much torque it is producing, if you want to actually quantify what is happening, if you want to solve problems based on what is happening, you should know where to consider mg. Till the last chapter, till work energy power, we never bothered about where to draw that vector mg. We always used to draw mg downwards. But for torque calculation, that perpendicular distance matters. Okay, so where exactly you draw the vector matters. Fine. One of you tell me, Does every particle of the rod experience weight or not?
Yes, sir.
Of course, every particle has mass, every particle experiences weight. Okay, so let's say the first particle is here, m1, then it will experience a weight m1 into g. Another particle is here, m2, it will experience a weight m2g. Okay, m3 experiences its own weight m3g, and so on. Let's say the last one is mn. It experiences weight like this, mn into g. Fine. So there are infinite mg vectors here. If you want to find out the net torque on this rod, you can't keep adding all these infinite torques. Okay, so what you will have to do is, you will have to replace this set of vectors with a single vector which produces the same effect. Okay, now how to find out where to draw that single vector? Okay, where should we indicate weight of a system to be acting? Let us discuss that. So what we want to do is, we want to replace all these vectors with a single vector which produces the same effect. Now, how did I decide that that single vector will be downward? Because all the individual vectors are downward, their resultant will be in the downward direction only, no? So that's the resultant that we want. Now, first vector's magnitude is m1g, next is m2g, so on up to mng. If you add all of them, you can directly add, because all the vectors are in the same direction. You can directly add their magnitudes. If you put all of them together, it becomes the total mass multiplied with g. So that's the net force. Okay, but we should ensure that the point where you show this net force to be acting, or the point where you apply this net force produces the same amount of torque. Okay, we should ensure that. Fine. Now, how do we find out at what distance you must apply this force, or you must assume this force to be acting? You should find out the net torque first. Now, let's say m1 is at a distance x1 from the axis, m2 is at a distance x2, m3 is at a distance x3, and so on. Mn is at a distance xn from the axis. Then the torque produced by the first particle's weight will be m1g into x1. Torque produced by second particle's weight will be m2g x2, because that perpendicular distance itself is x2. So on, torque produced by the nth particle's weight will be mn g xn. And all of them produce torques in the same sense, based on what we considered. Suppose there were some forces on the left side. Okay, let's say the rod extended on the left side as well. Then automatically, like if you consider a weight here, this produces anti-clockwise torque. These weights produce clockwise torques. That left side weight produces anti-clockwise torque, isn't it? But the x-coordinate will take care of that. For the particle on the left side, the x-coordinate will be negative, so torque will come out negative. Okay, so we don't have to bother much about whether we should add all of them or we should subtract some of them. Okay, you can simply add all of them. For the vectors which are actually supposed to be subtracted, the x-coordinate will be negative, it will take care of that subtraction. So the net torque here produced by all these mg vectors. Now imagine adding the right hand side, all terms on the right hand side. G is common. What will you be left with? m1 x1 plus m2 x2, so on up to mn xn. Remember seeing this term anywhere?
Position of center.
In position of center of mass, correct. X coordinate of center of mass is sigma mi xi divided by total mass of the system. So this bracket that you see here is sigma mi xi. So what can you write it as? Total mass into x coordinate of center of mass. Therefore, the net torque produced by all these small weight vectors is mg into x coordinate of center of mass. Therefore, where should you assume that net force to be acting? Wherever the center of mass is present, you should assume it to be acting there. And we know center of mass for a rod is the midpoint. So you can assume its weight to be acting through the midpoint for torque calculations. That is what all this proves. Fine. Remember, the point of application of weight of a system is actually called its center of gravity, which in this case is same as center of mass. But there are cases where center of gravity is different from center of mass. Now, how did we get center of mass here? By taking G common on the right hand side. Okay, if you assume we put G outside, then we got sigma mi xi in the bracket. What if G is not same everywhere? Then you can't take it out of the bracket. Then it will not be, then the then the point of application will not be the center of mass. Now you may ask, sir, why will G not be same for all particles? For small heights above the Earth's surface, acceleration due to gravity is same everywhere. But if you go too high above the Earth's surface, space, gravity decreases. Okay. So there can be situations where gravity is different at different points of the system. If gravity is different at different points of the system, then center of gravity means the point where you assume the total weight to be acting need not coincide with the center of mass. Okay, but for now, for the small systems that we are going to consider, like rod, block, disk, sphere, and all, center of mass and center of gravity will be the same. So remember this point. If G is non-uniform, means if acceleration due to gravity varies from point to point, center of gravity need not be the same as center of mass. Okay, but if G is uniform, then they are the same. So what did we learn now? First, in the previous problem, we learned how to replace a set of forces with a single force such that it produces the same translational and rotational effect. Same translational effect means net force should be the same. Same rotational effect means net torque should be the same. So it is possible to replace a set of forces with a single force. Okay. But if you know the forces individually, if there are only a few forces and you know at what distances they are acting, there's no point replacing them with a single force. Okay. But we can use that idea to express the weight of a system as a single force. Till last chapter, we used to write mg directly because till last chapter, we never considered rotational motion. Torque was not considered. If you want to find out torque, it matters where you consider the force to be acting. Okay. So if there's a force like weight of a system, which is very common, we have to consider weight of every system that we are going to analyze. So we know that each particle of the system has its own weight. So weight is distributed over the entire system. How to replace that with a single vector is what we have learnt. You can draw the single mg vector through the center of mass. It should actually be drawn through center of gravity, okay, which is same as center of mass if G is uniform. Okay, we'll stop it here for now. Next class, which will be tomorrow, we will discuss application of Newton's second law in rotation. Okay, Newton's second law in translation was applied as F net equal to ma. Okay, in rotation, the rotational analog of force is torque. So due to torque, what happens to the system? All that how to find out and all we'll discuss in next class. So you should be thorough with calculation of torque first. And then remember this point that weight of a system can be shown to be acting through its center of mass if G is uniform. Okay, thank you all. We'll continue tomorrow.